Everyone, welcome back to my data structure series. Today we are going to learn order notations in the simplest possible way. No confusion, no heavy maths, just clear logic. By the end of the video, you'll be able to convert code into T of n. Find a big O very easily and understand a big omega and theta clearly. You may wonder why the reason we focus only on big O because of the guarantee, the worst case. In software engineering, we care worst case scenarios. The maximum amount of time that the software process could take to ensure that the system is safe. So that is the reason we care much for this big O. So big O is the celebrity here. Moving on, let us see what is T of n. Let's start from the basic. T of n means operations that your program performs. So simple words, number of operations that your program performs is T of n. For example, look into this code. This reads a for loop which says for int I equal to 0, I less than n, I plus plus, and I print high. So here we are just going to count how many number of time the main operation runs. Just count, it is n times. So here the loop runs n times, so T of n is equal to n. So the correct way of representing is T of n is proportional to n. So for better understanding and clarity purpose, I have written T of n is equal to n. Now let's try a nested loop. Look, there is a for loop and another nested for loop, and I am printing high. So the outer loop runs for n times and inner loop runs for n times. So the total is n into n, which is n squared. So T of n is nothing but n squared. Moving on to another example where I have int I equal to n. There is a while loop which checks I greater than 1, and inside the while loop I write I equal to I divided by 2. Each time we divide by 2, the input size is halved. Each step you see, the input size is divided into half. So adding to this is specifically a log n to the base 2. So this is order of log n. T of n is equal to log n. So instead of calculating every time, we can easily recognize by patterns. If it is a single loop, it is n. If it is nested loop, n squared. Divide by 2, log n. A loop plus log loop, it is n log n. So you can easily identify from such patterns. So this will make you solve problems very fastly. Right. So now from T of n, let's move to big O. So now suppose you have assumed that T of n is equal to 3n squared plus 5n plus 10. So we need to simplify it. So how should I simplify this equation? According to my big O terms, I should ignore constants and lower order terms. I should consider only the highest term. So this becomes order of n squared, big O of n squared. So big O is just a simplified version of T of n. Actually, you can consider big O as a set, right? Okay. So now there are three important notations: big O, big omega, and big theta. Big O representing the upper bound, big omega representing the lower bound, and big theta which represents the exact growth. So for the equation T of n is equal to 3n squared plus 5n plus 10, the best case, that is assured minimum growth, lower bound is omega of n squared. Again, the worst case, the maximum upper bound is order of n squared, big O of n squared. Since there exists an upper bound and lower bound which are equal, theta is again n squared. So I appreciate and request you all to look into my order notation part 1 video for better understanding. Right. So moving on into the mathematical formulas for order notations. Fine. So before getting into the actual formula, so the process is very simple. You take the code, count the operations T of n, identify the pattern and convert to big O or big omega or big theta. That's all is needed, right? Okay. So we'll move on to the actual notations or the formulas. Fine. Before getting into, you should understand two key functions, f of n and g of n, in terms of order notations. F of n stands for the actual running time of your algorithm. Fine. So what is the actual running time? It tells you how many steps your code takes. So we have seen few examples. This video, previous video, we have seen few examples. So everything depends on the input size n. This g of n is nothing but a simple function we compare with. Because the real f of n can be messy, like we have seen, right? 3n squared plus 5n plus 10. So you need to simplify it. We have simplified it in the previous slides. So g of n is n squared after simplification. So what you understand from this is f of n will be the real cost, g of n will be the simplified growth. These two terms are very important. F of n is the real cost and g of n will be your simplified growth. Right. For the same example, for int I equal to 0, I less than n, I plus plus print high. So n is equal to 5 means it runs 5 times. N is equal to 100 means it runs 100 times. So f of n is equal to n, right? What makes us to compare f of n with g of n? Because the exact time depends upon the computer speed, the system load and the compiler, where this exact time is useless for us. We concentrate on how fast it grows when n becomes large. So we compare f of n and g of n to understand the growth. So in this slide we have just tried to understand f of n and g of n. So you might think, why suddenly f of n and g of n here in terms of big O notations? Yes. So I call something as asymptotic notations. These notations describe the growth rate of an algorithm's time or space complexity for large sizes of n, which ignores constant and lower order terms. So getting into the big O, big omega and big theta formulas. So big O gives you the upper bound. Read the formula. Let's make things simple. We'll break down. Big O gives the upper bound, meaning after some point, that is the point is n naught in the formula. After some point n naught, right, f of n will never grow faster than a constant multiple of g of n. Now you understand why I have introduced f of n and g of n in the previous slide, right? So big O is the worst case, means after some point n naught, f of n will never grow faster than a constant multiple of g of n. So big O is going to give you the upper bound. Let's see an example. F of n is 3n squared plus 5n plus 10. So what could be g of n? We have seen this. G of n is n squared. For larger n, 3n squared plus 5n plus 10 is lesser or equal to 4n squared. Is it not? For larger n. So it is understood that f of n belongs to big O of n squared. F of n belongs to big O of g of n. Right? Done. So this is what is for the first case. So now let us understand the formula of big omega. So what does this mean? Big omega? This gives you the lower bound. So big omega gives you the lower bound. What is this formula stating is that after some point, f of n is always at least as big as g of n. It means that f of n grows at least as fast as g of n. I repeat, after some point, The point is n naught here in the formula. F of n is always at least as big as g of n. Take the same example. F of n is equal to 3n squared plus 5n plus 10. G of n is equal to n squared. For large n, f of n is greater than or equal to 3n squared. So we can say f of n belongs to big omega of n squared, or f of n belongs to big omega of g of n. The last. So this is the tight bound. So big theta gives you the exact growth. What does it mean? F of n is in between the two multiples of g of n, right? So according to the formula, f of n grows exactly like g of n, both upper and lower bound. So big theta gives you the exact growth, meaning f of n is between multiples of g of n. So growth is exactly the same, right? Take the same example. F of n is equal to 3n squared plus 5n plus 10. So you can say that 2n squared less or equal to f of n less than or equal to 4n squared. It grows exactly like this, right? So f of n belongs to theta of n squared. Fine, done. So to make things simple, so three symbols, asymptotic notations: big O, upper bound; big omega, lower bound; and big theta is the tight bound. Right. So we have understood the symbols and their meanings, right? So let us see simple examples. Right. The first one is a very important common example. Okay. So the example states this: int a is equal to 5, printf, I'm printing a. So this runs once, no matter n, right? So this is running only 1. So I say it's order of 1. The next example, for int I equal to 0, I less than n, I plus plus, printf high. So this is running n times, so it is linear, so it is order of n. The next one is a nested loop. For int I equal to 0, I less than n, I plus plus. That is again a for loop inside which says for int j equal to 0, j less than n, j plus plus, print high. Outer loop runs for n times, inner loop runs for n times, so totally it is n squared, quadratic, order of n squared. The next one is a while loop which checks for condition n greater than 1, which says n is equal to n divided by 2. So it is cutting the input into half each time. So it is logarithmic. So it is order of log n to the base 2. Another example of a Fibonacci series. Look. So this call explodes very slow. So this is a typical example of order of 2 to the power n, exponential, right? So what are the easy ways to remember the speed order from the best to the worst case? It is order of 1 less than order of log n less than order of n less than order of n log n less than order of n squared less than order of 2 to the power n less than order of n factorial. So the quickest concept trick that we all use for learning, teaching plus examination is this: big O is the upper limit, worst case; big omega is the lower limit, minimum growth; and big theta is the exact growth, the tight bound, right? So we have seen almost few important examples of finding big O. Stay tuned. If suppose you see that this video is helpful, please share, subscribe and like. Thank you so much. Happy learning.